afternoon we'll be discussing human-computer information retrieval, which is the intersection of information retrieval and human-computer interaction, two fairly well-developed subdisciplines within information science. To begin, this will be in two parts. The first part will give the motivation and some overview of HCIR, and then close with an example from a system that we've been developing over the last several years. And then the second part will use a different example from yet another system with video content, and then we'll close with some reflections and implications. So here's the basic idea, or the message behind the concept of human-computer information retrieval. IR, or information retrieval, and human-computer interaction, they're related fields, but they're distinct. And they've had fairly strong traditions, some would say stayed, and they've been, I think, integrated, energized, or really jolted by the World Wide Web. And I'll say a little bit more about that in a few minutes. The intersection of these fields is really interesting because it offers new possibilities for really high impact research and development, especially for web IR and digital libraries. So that's sort of one of the main motivations. The challenge is in integrating the human and system interaction, and this is what we might call something like a symbiosis kind of goal, in which we'd like to have a symbiotic relationship between the human users and the systems that are increasingly capable and interactive. I won't say intelligent, because they're not, but they begin to emulate or simulate some semblances of intelligence. And the notion is that people are continuously engaged with information. It's not just, oh, I'm going to sit down and, at the workstation and do my XYZ search engine search right now. That's part of my ongoing work, my ongoing life, a good part of which is at some sort of workstation. So let's start with the information retrieval end of things. So here what we have is kind of the classic model of information retrieval. And this has gotten us very, very far over the last half century. The basic idea here is that we have the document space. This is all the information that ever existed or can exist in the world. And we have the query space. This is all the possible questions that ever could be asked in the past, right now, or in the future. And of course, those are sort of theoretical constructs. The notion of information retrieval is that in both those cases, we have some sort of sample. So for the document space, in today's world, the sample might be the World Wide Web. Well, that's huge. It's a lot of stuff, but it's still only a sample of the complete document space. Likewise, for the query space, the sample we're usually interested in is my query, or a small set of queries in the case of things like TREC, or Text Retrieval Conference, where we're trying to test a whole variety of queries across different systems. So these are the samples we start with, and from there, the key to information retrieval is to try and establish some way of making comparisons between the queries and the documents so that we can say these ones match and these ones don't. Okay? So in order to do that, for the samples of the documents, we create what I'll call surrogates. So these are representations for that document space. So a representation for a database might be the data dictionary, or the entity relationship diagram, the various tables, the fields that compose those tables, and so on. In the case of the World Wide Web, it might be a big inverted index of the various websites that particular search engine has crawled and created this index for. Usually, the samples will be made up of things like terms. So in the classic retrieval setting, what you had is a set of terms, and those may have been just keywords that were manually assigned, or they could be automatically extracted in today's world. Very often we represent these as vectors, and In the case of sort of the classic vector space model for representation, what we would have is all of the possible terms in the entire corpus make up this very long vector, and for each document you then just go in and say, does the term occur or not? That's the simplest example. So you have this big long vector that has a bunch of ones and zeros in it that represent that document and the occurrences of the terms from the entire corpus of terms in the document space. So that's one way to do this. Of course, there's more sophisticated things we can do to start to add weights to those values rather than having them just be ones and zeros. And so there's people write entire dissertations on just that particular issue. Likewise, on the query side, we also have a surrogate for the query, because the query, if we think about sort of the classical Taylor model of how people express their information needs, there's my real need, then there's what I can sort of think about and articulate and get out to the system, and then there's that compromise need of, well, I can't actually say it that way, I have to articulate it to the system in a certain sort of way. If it happens to be a database, it might be through an SQL type query. If it happens to be in a dialog search, it might be through some sort of very specific query format. In the case of, say, a Google search or a live search or a Yahoo search, it can be just plain text. So these expressions, or these surrogates for the queries, now need to get matched onto the expressions for the documents. So basically, the essence of information retrieval becomes the matching algorithms. How do we do comparisons? How do we actually do matching? This is the usual secret sauce of the search engines today, and things that they are quite guarded about in terms of how do they actually do the matching or the ranking, right? And so enormous amounts of work go into this, and there's literally billions of dollars at stake in terms of coming up with better matching algorithms. So we have the representation problem on both sides, and we have the matching problems. Now, this is a very powerful paradigm, and it's driven this research for literally a half a century. It's been successful in many respects because there's been an evaluation metric that, from an engineering point of view, people can say, this system does this better than that, or this algorithm works better than that, because we can measure it, and we have this evidence. Now, the effectiveness measures are these things called recall and precision, and they are numbers that represent recall. This is the proportion of all the relevant documents that actually get marked as relevant or retrieved as relevant. And precision, which is the proportion of the things that do get retrieved that actually are relevant. These tend to be inversely related, and so what we're trying to do is move both of them up as far as possible. Now, these are relatively problematic for us because the concept of relevance is is subjective. And so we usually have judges who make these assessments, or we create algorithms that estimate those relevances automatically. And then we can use the recall and precision measures to actually compare systems. So this is a great paradigm for getting us to where we sort of are today. And the claim is that, well, this has gotten us to a point where we've been able to create powerful search engines for known item kinds of queries that work fairly well. The challenge from my point of view is, of course, getting us beyond that to the more exploratory, more ongoing, more learning type of queries that are not just posed at one time, but are complicated and take place over a very long period of time. So what's driving some of the changes that sort of make us question this classic paradigm as being powerful enough to take us to the next step? Well, first of all, content themselves and the queries have changed. The document spaces and the query spaces are no longer just made up of text. We've got statistics and images and music and computer code and streams of data coming back from instruments in space and sensors in the environment. biochemical sequences and proteomic data that's being collected. Moreover, it's not just that there's data that's not just text, but it's also multimedia. So we start to mix these things up. So you've got data that's both statistical and video all mixed together. And it can be multilingual as well, so we can't just deal with a single human language anymore. Now, if that weren't bad enough, the really bigger challenge in my mind is that this content has become or is becoming more dynamic. This sort of has two kinds of related heads to it. First of all, it's temporal. The things that are changing constantly, blogs and wikis and sensor streams from the environment, these are things that are constantly being updated. And so what you can't do, as you could in the classic traditional sort of systems, is to go and create your index using lots of computer time. Then once you have the index, now it worked for a very long time. But when things continuously change all the time, you have to continually rebuild those indexes, and that's very expensive computationally. So some of the sort of the basic infrastructure that used to work fine for relatively, the literature grows pretty rapidly, but nothing compared to what's happening now with these kinds of very dynamic environments. So our classical approaches to fairly small changes in the overall corpus won't scale up or apply. The other kind of dynamic is that in addition to things changing, there are behaviors in the content. There are conditionals, computed links or recommendations that are being made based upon a certain set of events that have happened. Somebody bought this, somebody else bought that at this particular time. Therefore, the next recommendation is different than the one you would have had yesterday. Likewise, the computed link idea in which where you end up or what results get displayed depend upon something that happened previously or something, in the case of a user profile, that has changed and has been articulated to the system. So the upshot of this is that content relationships have evolved. We've got hyperlinks between content, we've got all sorts of new metadata that's either static or being generated automatically and constantly changing, and we've got aggregations of both of these things. So this complicates our content relationships building, our surrogation, if you will. Digital libraries or shariums, these shared workspaces that are increasingly evolving, personal collections, are all being put into the mix. So it's not just a well-understood, well-defined kind of corpus anymore. These are things that some of which are carefully curated and have very special kinds of retrieval hooks built in. Others are totally idiosyncratic and need to be dealt with fairly ad hoc kinds of tools. Basically, content is now acquiring history. And this leads us to the need for contextual retrieval, not just this matching of the query of the moment to the sort of relatively static corpus of documents of the moment. So some of the responses to this trend in content are listed here. Link analysis is probably one of the biggest advances we've had, in that we've been able to begin to leverage not only things like the author's words as sources of evidence, or the indexer's words that assign terms to these documents, or the query, the searcher's query words, but the links that exist among documents are now being leveraged. And this has given us sort of a whole new source of evidence. Classical sources of evidence, the author's words, which led us to the full text retrieval capabilities. Index or abstractor words, these were the classic kinds of bases for online public access catalogs and the workhorse retrieval systems of the 60s, 70s, and 80s. The author's actual citations or links, in the case of citations, the Institute for Scientific Information's citation indexes have long been used to enhance queries and do citation programming, for example. And of course, in today's world, the search engines pretty much all now use some sort of link analysis, either through PageRank or some similar algorithm, to use the in-links and the out-links that occur on individual pages to actually add some additional evidence for the efficacy or the importance or the popularity, really, of those individual documents. And so the document representations become related to these PageRank kinds of values. Now, there's also the reader's search paths themselves. These are the things that actually occur as people use these systems, the traversals, the actions they take. They build up and they lead to either recommenders, recommendation systems, or opinion miner types systems based upon the fact that many, many different people have done a certain kind of activity or follow a certain path. We use the wisdom of crowds kind of notion to actually, again, enrich the document indexing in the document space surrogates. Social tags are also increasingly popular. So the delicious Flickr kind of tagging that individuals do. These are not professional indexers, but there's a lot of people tagging, and so you can begin to look at dozens or scores or perhaps hundreds of tags and add some additional value to try and create more germane surrogates for the different documents. And more, there are various kinds of machine-generated features and relationships that are being created, relationships that machines are discovering either through user behaviors or through co-occurrences or relationships that exist through corporations or through universities or through institutional kinds of patterns that are also being added into the mix. Now, this leads to a couple of key challenges. What are the new relationships that we can leverage? And I think this is an entirely new and rich area for us. I would claim that a fundamental challenge of information science is the discovery of new kinds of relationships. I mean, we need a theory of relationships that allows us to then look at certain kinds of possible linkages and see if they're useful to us, and we can find a way to take advantage of them for the purposes of retrieval and human learning and information seeking. Does it matter that two people were alive at the same time or born on the same date? Those are relationships. Could we use that in any way? Well, it's a little hard to imagine how that might actually be helpful. But there probably are a lot of other relationships we haven't thought of yet that we might be able to create or mine or take advantage of to try and add to our sources of evidence to then lead to this fused set of document retrieval systems that we create. Now, I said fused, and that's actually the second challenge here. So you've got all this evidence. How do you put it all together? How do you actually take these different sets of evidence and weight them, or do you just equally weight them? Do you do it in a linear fashion? Do you have some sort of schema that is dependent upon other kinds of conditions? I mean, this is complicated and there's a lot of permutations, and so the weighting schemes for data fusion becomes another grand challenge. So these are the two kinds of problems that many people in the information retrieval community are addressing today. Now, let's turn our attention a bit to the human-computer interaction world. So here's sort of a classical view of human-computer interaction. In this model, you have sort of the human and you have the machine, and the idea is that there's an intermediation process between the human and the machine that we call the interface. This was too big to actually stretch across the whole screen, so imagine it as this sort of loop, not quite a loop, but a linear kind of process. And there's interaction back and forth. So in terms of the human, there's internal processes, and there's sensors, and there's effectors, and likewise in the system, there's internal processes, and there's effectors, and input and output devices is what we would call them. Internally, we usually call the human side of the internal processes mental models. That people have mental models either for a system or for a process or for some concept, and that's what allows them to actually understand things and to make projections and to add to new knowledge. In the machine, we certainly don't want to call them mental models, so sometimes they're called conceptual models. These are actually the models that programmers or the designers of these systems have for either the user or for the task. And so those conceptual models are built into the system and give it its kind of rules of operation and the kinds of functionalities that the software offers. Now, the interface part external to these I/O devices within these the human and the machine are conceptual interface mainly, and these would be the physical interface. And these are really rules for exchange. So human rules for exchange have things like language, and we have rules for language. Like you can only talk a certain speed, otherwise you'll go over your tongue like I just did, and you won't be able to get things out and people won't be able to listen. So there's a range of how slow or fast we actually like to hear things. There's also the concept of sort of duplex, that human interaction tends to be half duplex. We're polite. And if we listen to somebody else talking and then when it's our turn, we take our turn and we go back and forth, and only one person usually is talking at the same time. Now, machines, on the other hand, have different sorts of rules. And they certainly can be full duplex, because machines can sort of send signals back and forth at the same time. And they're pretty impoverished when it comes to the richness of the language, and so we have things like commands or menus that actually limit things even more. Direct manipulation sort of gives the closer coupling between the human and the system, in that every action, not just a typed-in command, is a message to the machine, and the machine responds in a very fast way. So this is kind of the classic model, and of course there's this noise issue that all the problems that can go wrong here technically, but mainly mentally in the case of the human user or the designer's poor articulation of the conceptual model. So this is a user-oriented model. It's driven the research and development, again, over the last, say, 30 or 40 years. And its evaluation, unlike the recall and precision-oriented IR world, tends to go toward either the time on task, time to actually execute a task, accuracy, which gets a little sticky, how accurate some task has been completed, and satisfaction and a host of other subjective kinds of self-report measures. Now, the trends in human-computer interaction have also been strongly influenced by the World Wide Web. So the first decade of the web was actually pretty traumatic to HCI, in that, in a sense, it was a great equalizer. Many people now who didn't use computers before now had a reason to use the computer and were empowered to use the computer. But because it was a stateless system, the actual kinds of user interfaces that depended on these very nice couplings between your past action and your current action disappeared in the web. Because there wasn't state, the system couldn't tell what you did in your last move, and so you couldn't have very rich models. And so in a sense, the web kind of set back some of our interface development work, but it actually opened up whole new communities of people. So in the long run, it's of course been a great thing. It's also opened up the problem of universal access. So it's one thing if you only have to sort of create a system and a user interface that works for 1,000 people. But when you have to try to create something that works for 200 million people or 1 billion people, quite a different challenge, because now you have an entire range of people, and especially if you want everybody to have access, then you have to work much harder to try and design systems and user interfaces that will meet the needs of people with special kinds of needs. The platform independence drive is actually pretty important in human-computer interaction, because you can't really, if you have 1,000 different platforms out there, it's very difficult to predict what kind of screen people have, what kind of layouts are going to be available to people, what kind of input devices they'll have. And so you really have to sort of come down to some small number of lowest common denominator type of standards. And so going across platforms is cost effective for designers, and so what we like is to try and find things that you know, are not so sort of proprietary to a certain kind of hardware system. This has led to very enhanced browsers in today's environment, and Ajax-like technologies, which do not require the back and forth from the server quite as much, so that you can do things on the client side, like refresh the screen or open a pop-up window and refresh that pop-up window without having to go back to the server and having a 500 or a millisecond or a second or two delay. So this is something that's, you know, we're trying to break out of that web as a stateless kind of environment through things like Ajax. We've tried to think about concepts like interface servers. Can we create interfaces that themselves sit out there in the web cloud and that people can pass through to go to Amazon or eBay or Google or whatever they happen to want to use, and use the same interface rather than having to go to a different interface every single time? And of course then the Web 2.0 social awareness development is also quite exciting for HCI, and you know, the fact that the user is not alone, and so you're now trying to design for a user that's actually acculturated in a distributed space, and you may be able to take advantage of other people who are also in that physical space at any given time. Whether that's an avatar in Second Life who is nearby, or it's a person halfway around the world who happened to have just done the same query. So, things change. And people change a lot slower than systems, but we do learn. So some claims here. The web and TV remotes have, I think, legitimized browsing as a human-controlled information-seeking kind of activity. So in the old days, if you were trying to browse for some information, you probably got your hand slapped and said, "Oh no, you should learn to do a nice, clean, crisp Boolean query." That's the way to really be efficient. It might be more efficient, but it also is quite can be quite limiting. And so the browsing is now sort of expected in the general population. It seems to me that we can't just expect the machines to do everything. We need them to take some responsibility, and part of that is to not just expect to put in our 1, 2, 3 word query and expect to just magically have the best result come back ranked #1. I mean, sometimes that happens, and that's great. But most of the time, you need to work a little harder. But if it's worth answering, then it's worth doing a little bit of additional work. And so this notion of responsibility on both sides is something that I think we need to promote. Another important sort of message that certainly the information retrieval community is beginning to understand, and the HCI community I think has at least given good R&D direction to, is that people don't really want retrieval. I mean, what they want is understanding. They want to solve their problems. They want answers, or they would like some fodder for that problem-solving process that they're currently engaged in. And so it's not, no one just says, "I'm going to go do some retrieval today." It's always embedded in some sort of larger task. And so what we really want is understanding. And just delivering a bunch of links to a bunch of web pages doesn't quite do it, unless it's really just a fairly pedestrian sort of known item type search. Now, it seems to me that one of the reasons, or the ways that we as humans have changed, and as a society, is we have a much higher level of technical literacy. Now, many of us would say, well, that's not, we need to continue to work on that because it's very poor literacy. But in fact, it's much better. I can remember teaching people how to use a mouse, and there would be people who would actually pick it up and do something like this. And nobody, I think, today would do that. Certainly not in the developed world, at least. There's a whole sort of understanding about this technology that is in place that we should be able to leverage a bit. The notion, the real challenge then, is to try and build upon that literacy so that we can get people to think with the tools, not to have the tools think for them. Some of the responses that research and practice that have emanated from these kinds of developments. Adaptive techniques in the World Wide Web, the relevance feedback, the notion of being able to actually give people a response and say, do you like this? Or would you like more like this? Now, if people would take the time to actually respond to some of that, they get much better results more quickly. Query expansion, automatic query expansion tends to be a little bit dicey. But if you can get people to intelligently expand queries by making selections from reasonable sets of alternatives, you can get quite rapid improvements in search results. There's a lot of work on user modeling or creating profiles. In the classic library science sort of world, we call these selective dissemination of information services, where you try to anticipate people's needs and you feed people things before they even know they need them. I used to have a librarian who was amazing at this. He would put stuff on my desk or in my mailbox that would be dead on target to things I was working on, and I would totally have missed them. But through his powers of looking through the literature and scanning lots and lots of different kinds of materials, he was able to anticipate my needs and meet them in really interesting ways. And I think we'll continue to see some of that done in the kind of filtering services that are on the web today. The challenge there is that people tend not to want to do much training. They don't want to spend the time to create those profiles. Whether they can be created automatically through observation leads to privacy issues. So we have these kinds of trade-off situations that both motivate and inhibit research and development. Recommender systems are sort of one kind of answer that actually has had a good amount of influence. These things, for example, in Amazon, when you buy a book and then you go back later and they say, well, you bought that book, here's a book very much like it. Or lots of other people bought this book and they also bought these other books. And so there's these sets of inferences made either by your specific behavior patterns, the social group or the whole community's behavior patterns, or in some cases, in the case of explicit models of recommenders, actual reviews that people post. So you have both the implicit, automatically computed, and the explicit, done by usually humans, models for recommender systems. Another approach is that you just try to capture everything. And so the My Life Bits project at Microsoft is a good example of this, in which really trying to capture all of my communications, all of my interactions with the web, all of my phone conversations, all the things I do in order to better make them accessible to me at some later time is quite an interesting one. Seems to me that digital libraries in general and things like My Life Bits might be some of the electronic treatments for things like Alzheimer's and other sort of forms of dementia, in addition to, of course, the life science type of solutions that we're aiming toward. Now, another approach here is human tuning of IR systems, in which that people actually continuously work to improve the system. And I think this is actually in place in all the search engine companies, where every day there's some new spam kind of activity that is defeated or anticipated by people who tune the system, or there are new events in the world that take place that then change the ranking for queries related to those kinds of events. And so these are things in which humans and machines are working together to try and get better, rather than saying, oh, we're just going to let the machines do everything, or, oh, this is just a human problem, let the users worry about that. Now, our approach is what I've highlighted here to this people trend is better user interfaces. And so 2 kinds of ideas are what we've been particularly working on: dynamic queries and the Agile View framework for doing design that gives people multiple views. And we'll say more about this in a few minutes. To sort of summarize, though, the basic HCIR model goes something like this. Instead of thinking of IR as this kind of matching of documents and queries that the system does, and humans just kind of pose the queries, we want to think of information retrieval from the perspective of an active human who's got information needs, not queries, and skills. So let's get the human skills involved here. Powerful information retrieval resources. These are the digital libraries and the web resources that are out there. And those could include other people, not just these documents. They're all situated in global and local kinds of communities that might also be leveraged here. And all of this evolves over time. Now, if you think of IR or HCIR from this perspective, it's a much bigger long-term sort of challenge, but one that hopefully will lead to a much better kind of information-seeking environment in the times ahead. Some of the features for this kind of vision for HCIR: get people closer to the information they need, right? Closer to the meaning. Involve information professionals of all sorts in the process, so it's not just the human user and the machine, but we're embodied and embedded in a social context, and that social context has a lot of professional support systems from the IT point of view, from the information professionals' point of view, that we should be taking advantage of. And users need to increase their responsibility as well as their control. We clearly want to give them control, but they also have to actually have reasonable expectations and take responsibility for their activities. We want to leverage a more demanding and knowledgeable installed base of users. People are expecting more because they've been satisfied for some of the basic needs. And so how can we get to the more difficult challenges is something that needs to be built into this HCIR model. We really need to think of these services, these digital libraries, as extended memories and tools, so both personal and shared. The personal kind of personal information management system sort of sense. The shared kind would be in the institutional repository or the cultural institution sense of libraries and museums and archives that belong to all of us. And finally, to consider information from kind of a life cycle perspective rather than just that static, here's where it is right now sort of finished document, from the creation to its use and its various versions as it's passed through, how it relates to things in this current state, and how it can be persisted and preserved over long periods of time. So here's a different sort of model. Notice the figure from before is now turned on its side and embedded in this larger view of human-computer information retrieval, in which the human is really trying to get closer to the world that they need to interact with and understand. And what facilitates that is a powerful information retrieval system, a physical interface of various sorts of devices, and a conceptual interface of rules that make it easier, not harder, to actually work with the physical devices, the underlying back-end systems, and allow this to, in a sense, become more transparent is the ultimate goal. The key challenges here, linking the conceptual interface to the system back-end. This might involve generating metadata for documents so that they can be more easily described and retrieved and understood once they've been retrieved. Alternative representations, providing a different representation. I mean, what we'd like to be doing here is information alchemy. We'd like to say, well, you're a visual learner, we're going to turn this into a visual representation. Or you're an auditory learner, we're going to speak this to you. Or you're a really good reader, we're going to give you the text. Likewise, elegant and agile control mechanisms that allow people to quickly move across these different alternative representations. This is the essence of the Agile Views framework. It's that we really like to have alternative representations and easy mechanisms for changing across those mechanisms. We'd like to actually raise literacy and involvement without insulting or annoying people. Try and get people to give a little more or get a little more involved. We certainly want to leverage human intelligence and skill. Get them engaged, and their engagement is going to improve the system. We want to move beyond retrieval to understanding. That involves some contextual retrieval, and we do need new evaluation measures, which I will speak to in a bit. So with that, I'm going to move to an example. This is an example of something we call the relation browser. It's a generic user interface that's been used for about 36 different kinds of database applications over the years. It works really well if you have a well-structured database kind of back-end. What we've been trying to do is to apply it to ill-structured or semi-structured web-based environments, in this case the Energy Information Administration's web pages. I'm going to shift to an example here of the Bureau of Labor Statistics and show you how this works. So this is the Bureau of Labor Statistics website of about 1.5 years ago. What we've done is to partition the web pages in this fairly large corpus of 60,000+ web pages. This is really based on the HTML web pages, which is something on the order of 25,000 web pages that were crawled. And we put them in these categories. And we call those facets. The facets really of interest to us, because this is the hardest problem, is topic. How do you put things automatically into topics? And so here are some topics, and the way the relation browser works in general is, let's say we're interested in prices. Just at the start, I see that of the 25,000 or so pages, there's 713 pages, you can see that right up here with the 713, that relate to the topic prices. When I hover the mouse over prices, what I've now done is a query. Only it's a query by just moving the mouse. Right? So it's not something that's permanent. I didn't have to go back to the server. This is all on the client side. And I see that for my 713 price web pages, that they're classified into these different categories. Let's go with geographic coverage. I see that 40 of them are classified as being at the state level rather than at the international level or the sub-state level. I can continue to browse, or I can freeze that by doing a single click. Once I've done a single click, now I can continue to browse, and let's say I'm interested in just those state ones. I now see that, gee, in the year 2004, there were only 12. Because if I want all the state ones, all 40, in 2004, there were 114. So let's take the 40 state ones, and if I click search, and now it's gone out to the server, and it's pulled back the metadata from each of these web pages. And we can see that for prices at the state level, here are some web pages that will presumably give me information of prices at the state level. And if I pick... And so this is just a general way that the relation browser works. And what I'd like to do now is go back to the slide presentation, talk a little bit about the goals, and then explain some of the automatic metadata generation work that we've done. So our goals here is to facilitate exploration of relationships across different data facets. That's really sort of the high-level goal of this kind of tool. There are many other tools out there that work very well. A well-known one is the Flamenco system, UC Berkeley, Marty Hurst's work and her students. There's also commercial systems such as Indica that are used in commercial environments that are facet-based. Facet-based systems work very well as long as you have a good structure underneath, and that's why discovering metadata is really crucial for these kinds of interfaces and retrieval systems. We want to display alternate partitions of the database just with mouse actions. So the idea is brushing or hovering is a query form. We want to support string search within partitions so that you should be able to actually do either full text, or in the case of the relation browser, we really just do field string search at this point in this version of the system. And we want to serve as an alternative to existing search and navigation tools. I don't see this as being really replacing things, but being an alternative to, or something that would be used, say, before or after you do your basic search engine kind of search. Some of the basic principles here, we want to juxtapose the facets with anywhere from 5 to 15 categories per facet. We're very constrained by screen real estate. If you have to scroll, this is a dead in the water kind of application. You can't have any scrolling here. You want everything to be very dynamic and fast. So that limits things to the number of rows, if you will, or categories within a facet that we can handle. Topic is really one of the most important facets in all kinds of applications, and so that's where we've spent most of our research effort. The interaction principle here is dynamic exploration of relationships. And it's database driven that promotes scalability and flexibility on the back end, but it does require this systematic metadata. There's some obvious kinds of limitations. The evolution of getting the metadata to the client side requires a pretty good network connection. But once it's there, then it gets fast, and you can have this sort of under 250 millisecond kind of response that you really need to make this be smooth. The user expectations and preparations. I mean, just because this, you look at this doesn't mean you know how to use it. So it doesn't take long, 5 seconds, 10 seconds, to sort of get a sense of how things work. Then you can start to figure things out. It's kind of like a video game where you look at it and you kind of watch it in demo mode, and then you go, oh, I see what's going on, and you can pick it up. So that's the sort of thing we think is needed for this kind of tool. Getting the metadata and mapping it to the relation browser database scheme is really a huge kind of effort, and that's where we're going in a second. So here's what's our sort of model of one way to automatically generate this metadata. So there's sort of these various steps of acquiring the data, building representations, doing some filtering, projecting that very large representation typically onto a smaller dimensional space, doing some clustering, naming, because clustering doesn't tend to name things. It tends to name things like number 7 or 0.003496. And so actually giving human understandable names, assigning these to the RB schema, and importing it into that application. So this is the process. There's actually a metadata mining toolkit that's available for download. John Elsis and Miles Ephraim get the credit for putting this together and making it open source accessible. So the acquired data set, and now we're talking about some sort of classic information retrieval type work. You crawl the websites using some sort of crawler, and this in the case of the BLS, we just did the HTML pages because we're trying to do things as quickly and easily as possible. We mirrored this locally, so we actually downloaded these. This yielded about 23,000 HTML pages. Then we cleaned the data, we removed sort of non-alphanumerics, we made everything lowercase, we went into WordNet to validate some of the words that were questionable, and then we played around with some stemming or non-stemming and eventually used the Porter stemmer. The second kind of step, once you've now grabbed this data and did some basic cleaning, is to build representations. We've tried lots of different ways to do this. One was to sort of just select certain kinds of pages. The best example, and what we've actually implemented, which in the demo you just saw, was the BLS editor's desk. These are actual a little over 1,000 pages that were descriptive, they were well written, well structured, and so we were able to actually take advantage of some of that structure. Basic ASCII text, instead of doing full text, which we did try, We got actually better results just using titles, metadata tags if they're available, which they seldom are in sort of today's web environment, but link anchors. The actual text that points into a page is extremely valuable. I think the search engine companies certainly know about this and take advantage of it. We found that to be a very powerful set of evidence for our work. Once we've decided what pages to use and what parts of the pages to use, then we build this raw term document index, pages as rows, and terms as columns. And so there are about a little under 27,000 unique terms in this subcorpus. And then you either do frequencies or term frequency over inverse document frequency weights in the cells. And we use the TF-IDF values. Now that you've built this representation, which is basically this gigantic matrix, and it's pretty hard to sort of deal with such a thing computationally. So usually we want to try and reduce it further. One way to do that is to filter the data, get rid of the stop words, the general terms, the thes and us and so on. Domain-specific terms. So labor and the Department of Labor Statistics, or the Bureau of Labor Statistics website, may not be that helpful. Web and navigation terms, the back button is on everything, and so the word back or home, things like that, we took out. Now home, actually, I don't think we took out because I've had other meetings. Iteratively developed and refined. What that means is we didn't just sort of do this once. We did several iterations and runs. In fact, I would claim that this kind of work is what the catalogers of the future will do. They'll tune data mining algorithms. We did some term discrimination filters and tried a various number of them. We settled on sort of the classic Sultan interval, terms that occur in 1 to 10% of the documents across the entire space. And we found that that actually wasn't so good for our clustering. So then we later on went back and we augmented by putting the top 100 frequently occurring terms in the entire corpus. That helped a lot. We then established some various kinds of empirical thresholds, like it had to occur at least 5 documents, otherwise it didn't get included as a term. To further compress this, and this is critical, we then had to reduce the dimensionality further. We did several kinds of experiments. Principal components, standard statistical technique, latent semantic dimensions, anywhere from 50 to 100 LSI n values. And we tried some work with independent components analysis. None of these were magic bullets. They all sort of had their pros and cons. But the result, in any case, is to reduce us to a narrower, smaller term document matrix. Now, once we have that smaller term document matrix, now we can actually use clustering algorithms and run them in sort of reasonable amounts of time on reasonable kinds of desktop machines. So we started with k-means, a standard clustering technique, with k being much less than 100. We were trying to get our k value, what we'd like to come up with our clusters in the order of something like 10 or 15. Because remember, we're going to put this in the relation browser, and we don't have that many rows we can deal with. So the categories are small, and those categories are going to map onto these clusters. So we were aiming at something like 15, 16 for our k values here. We also used expected maximization algorithm, machine learning technique, EM. And this is a little more interesting because it actually yields a probability distribution for these documents over the clusters, so that we actually had not just it's there or it's not, but the probability of it being there or not, so that we could associate a document with each one of the clusters. Now we really wanted to evaluate the clusters and name the topics, and this is where we had to have human intelligence involved. You can do things like take the centroid of the cluster and then find the most frequently occurring term in that centroid and make that the name of the cluster. That's sort of a classic approach. There are lots of others. But we decided we really wanted humans to name these things. And so what we did was we created usable output. We created a web page that took the clusters and the number of documents in each. And for each cluster, we gave a list of the top most frequently occurring terms and a list of the top log odds ratio terms. These are the terms that were frequently occurring, but now down-weighted or up-weighted by their distribution across the document corpus. And we then had humans, our research team, anywhere from 3 to 15 people, depending on which trials we were experimenting with, to manually eyeball the terms, pick a cluster, and give a name based upon our human knowledge of what's at the Bureau of Labor Statistics. Okay, so that was the process in this step. Next, we want to assign these pages to topics, and here's where we took advantage of the EM model to say, well, the probability that this document belongs to this cluster that we happen to name prices is 0.8536298, or whatever it happened to be, and that's pretty high. So we're gonna put it in prices. The probability that it goes into one of the other clusters is 0.00007333, something like that. Well, we're not going to put it in there. So we have the possibility to now assign documents to multiple clusters. In most cases, though, they went easily into one topic based on some simple thresholding. So finally, after we've done this and we've named these clusters, it's now time to take this, put it into the database structure that the relation browser works on. And this is a pretty much forward kind of step. So what did we learn? Well, automatic classification works best when you got people involved. So we're not there yet in terms of being able to automatically classify things. I mean, systems like Clusty and so on do an interesting job of giving results that are clustered, but if you ever spend much time with them, there's always things that are misclassified or missing. Same thing happens when humans do this. But having the human and the machine do this together seems to work better, and that makes sense, and it goes along with this notion of human-computer information retrieval as a collaborative process. So now our idea is that the relation browser is embedded in this larger process of information seeking, and so instead of that other IR system, we have this kind of process embedded. Again, it's not what people have to necessarily deal with themselves, because it's part of this larger, hopefully transparent process that allows the human to get closer to the world they're interested in. Okay, so we're going to stop here, and we'll pick up with part 2 with the second example.